Welcome back to the Deep Dive. Today, we're going beyond just equations and really diving into the philosophical shock waves, kind of the philosophical earthquake caused by Einstein's theory of general relativity.
It's interesting because general relativity wasn't just this scientific revolution, it really was a philosophical earthquake. I mean, when you start messing with ideas like absolute space and time, you are bound to stir up some serious philosophical debate, right?
You're telling me we've got a pretty dense article here from the Stanford Encyclopedia of Philosophy.
Oh, okay.
And it really digs into how different philosophical camps reacted to this monumental paradigm shift.
Yeah,
It's like watching a boxing match, between these titans of thought.
it really is. And one of the first groups to really step into the ring were the machina positivists. And they were initially excited about Einstein's work because it seemed to support their idea of the relativization of inertia.
Okay.
It's a bit of a head scratcher, but it gets to the heart of how matter, motion, and gravity all kind of interact.
Okay, so let's unpack this a little bit. For
Sure.
those of us who haven't, brushed up on our Mach lately,
Yeah.
can you break down this idea of relativization of inertia?
Of course. So you see, Ernst Mach, he was a physicist and philosopher, was deeply skeptical of Newton's idea of absolute space.
Right.
He believed that a body's inertia, its resistance to change in motion, wasn't an inherent property of the object itself. Instead, he argued that inertia was determined by the gravitational influence of all other matter in the universe.
So instead of being this kind of fixed absolute thing, inertia becomes relative, dependent on the entire cosmic landscape of matter.
Exactly.
That's a pretty radical shift in thinking.
It is. And Einstein was deeply intrigued by Mach's ideas. In fact, he saw general relativity as a potential path toward incorporating this concept of relative inertia into a comprehensive theory of gravity.
So it's like everything's pulling on everything else in this grand cosmic dance, and that interconnectedness determines how objects move and resist change in motion. It's beautiful, really, kind of a profound concept.
It is. And now, where things get really mind-bending is when we look at what Einstein said about general covariance.
Okay.
He claimed it takes away from space and time the last remnant of physical objectness.
Wow.
That statement alone launched 1,000 philosophical dissertations.
Hold on, physical objectness.
Yeah.
It sounds like he's saying that space and time aren't even real. Can you help us unpack what Einstein meant by that?
Yeah. So this is where we stumble into the infamous whole argument. It's a philosophical puzzle that still keeps physicists and philosophers up at night. It's a bit complex, but in essence, it suggests that in a generally covariant theory like general relativity, you can't really talk about points in space-time as having an independent, inherent existence.
So it's not like you can point to a spot in space-time and say this point has these specific properties regardless of anything else.
Right. Because the properties of that point, including its metrical properties, think distances and durations become entangled with the distribution of matter and energy within that space-time.
Yeah.
It's like trying to describe a wave without the ocean. You can't have one without the other.
So space-time itself becomes this dynamic, fluid entity constantly shaped and molded by the stuff within it. It's almost like space and time are more like verbs than nouns.
That's a brilliant way to put it.
I like that.
And this, of course, flew in the face of traditional Newtonian physics, where space and time were seen as absolute and unchanging, like a rigid stage upon which the cosmic drama unfolds.
I can see how this idea would just send, shockwaves to the philosophical world, right? I mean, it challenges our most fundamental assumptions about the nature of reality.
It does.
I imagine the positivists, with their emphasis on observable phenomena, would have had quite a bit to say about this.
Initially, they were thrilled, right? The idea that space-time was determined by the distribution of matter seemed to fit perfectly with their emphasis on empirical verification.
He saw it as a triumph for their approach. But as general relativity developed, it became increasingly complex, and the gap between its abstract theoretical constructs and direct experimental verification, it began to widen.
Yeah.
This made some positivists uneasy,
So they were on board with relativizing time like Einstein did in special relativity with his thought experiments about trains and lightning strikes. But the idea of relativizing the entire fabric of reality, that was a step too far.
You could say that. Remember, this was a time when even the existence of atoms was still debated, right?
Yeah.
So a theory that questioned the absolute nature of space and time itself was a pretty big leap. even for those who prided themselves on embracing these radical new
It
ideas.
really highlights how revolutionary general relativity was,
I
right?
was.
It wasn't just a new theory, it was a whole new way of looking at the universe, like demanding a completely different philosophical framework.
Exactly. And to make things even more interesting, there's another layer to this McKeon story.
Oh, there always is. It involves what's known as Mach's principle, which essentially demands that the metric field, that's the mathematical structure that determines the geometry of space-time, right, is entirely determined by the distribution of matter and energy.
Okay, if I'm following you, Mach's principle is saying that the very shape of spacetime, its bumps and curves, are directly molded by the stuff inside it.
You got it. And this, again, challenges the notion of absolute space and time. It paints a picture of the universe as this self-contained system where matter, inertia, and the geometry of space-time are all intimately interwoven.
That's a pretty profound concept.
Yeah.
But did general relativity actually manage to fulfill Mach's principle?
Right.
Did it really succeed in relativizing inertia in the way that Mach envisioned?
That's a question that is still debated today. You see, Willem de Sitter, who was a Dutch astronomer, showed that Einstein's field equations actually allowed for solutions that described a universe completely devoid of matter.
Wait, so you're telling me that even without any matter to shape it, spacetime could still exist and have a structure? That seems to throw a wrench into the whole idea of Mach's principle.
Right. It raises all sorts of questions about the exact relationship between matter, inertia, and the geometry of spacetime. And those questions are still being grappled with, by physicists and philosophers alike.
It seems like general relativity, while inspired by Mach's ideas, ended up opening up this whole Pandora's box of philosophical questions that went way beyond what even Mach might have imagined. It's a bit ironic, wouldn't you say?
Absolutely. And to add another layer of complexity, Einstein himself seemed to move away from positivism as his research progressed. He even famously called Mach a deplorable philosopher later in life.
Oh, the drama. I guess even brilliant minds can have their philosophical fallouts. So I've got this fascinating mix of positivism, relativity, and a dash of intellectual tension.
Hmm.
What other philosophical camps entered the fray in response to general relativity?
Well, let's shift our focus to the Kantian and Neo-Kantian interpretations, which offer a very different and perhaps even more surprising take on the implications of Einstein's groundbreaking theory.
Okay, here's where it gets really interesting. We're about to see how a theory that seems to challenge the very foundations of Kantian thought was actually embraced by some Kantians as confirmation of their views.
Right.
Talk about a plot twist.
That's the beauty of philosophy sometimes. Even seemingly contradictory ideas can find common ground, and the Kantian and Neo-Kantian responses to general relativity are a perfect example of that.
Well, I'm definitely ready to dive into this Kantian rabbit hole. Let's see what philosophical gems we can unearth.
So to grasp the Kantian reaction, we need to kind of remember that in Germany at the time, Kantian philosophy, particularly the Neo-Kantian schools, really held immense sway.
Right, and for Kant, space and time weren't like objective realities in themselves, but rather these forms of intuition, kind of the fundamental lenses through which our mind structure, our experience of the world. How did that square with general relativity's view of space-time as this malleable, dynamic entity? I mean, it seems like a head-on collision.
You can imagine the shock waves, right, that rippled through these Kantian circles when the idea of gravity warping space-time hit the scene. At first, many Kantians tried to downplay or reinterpret general relativity to try to fit it within their existing framework. It was like trying to squeeze a square peg into a round hole.
Yeah, I can almost picture them frantically trying to shield Kant's ideas from this seemingly radical new physics.
Well,
What were some of the strategies they used to try to reconcile these seemingly opposing views?
Oh, they got creative. Some, like the philosopher Ernst Sellian, argued that Kant's ideas about space and time only applied to what he called intuitive space, which was separate from the measurable space and time that physicists were dealing with. It was a way of saying, look, Kant's talking about something completely different, so there's no conflict here.
A clever way to sidestep the issue. Did other Kantians try similar tactics?
Absolutely. Another Kantian philosopher, Ilse Schneider, argued that Kant had essentially predicted, in a way, this non-Euclidean framework.
Okay.
She pointed to Kant's statement that the space of three-dimensional Euclidean geometry is the space in which Newton's gravitational law is valid.
Right.
And she suggested that this implied that Kant recognized the possibility of other geometries.
So she was saying that Kant's philosophy was already flexible enough to accommodate these these new geometric concepts, that Kant was ahead of his time in a way.
Precisely. She even pointed to Einstein's concept of a finite but unbounded universe as being compatible with Kant's ideas about the limits of human reason. But while these attempts to immunize Kant's philosophy were intriguing, not all Kantians were content with simply reinterpreting or sidestepping the issue.
So some were willing to stare general relativity's challenge right in the face and reevaluate Kantian thought in light of these new discoveries. That's pretty bold.
It was. Many realized that the most vulnerable part of Kant's system was his transcendental aesthetic, the part that dealt specifically with space and time as these forms of intuition. General relativity, with its use of non-Euclidean geometry, seemed to directly contradict Kant's claim that space had to be Euclidean. It was a major philosophical dilemma.
Yeah, it's hard to maintain that space is inherently Euclidean when you've got a theory showing how gravity can warp and bend its very fabric. Did these Kantians just throw in the towel and abandon Kant altogether?
Some did, but others saw an opportunity to kind of refine and update Kant's philosophy rather than discard it entirely. For instance, a philosopher named Karl Bollert argued that general relativity didn't invalidate Kant, but actually clarified his position.
Hold on, how could a theory that seems to contradict Kant actually clarify his ideas?
So Bollert argued that instead of seeing space and time themselves as the a priori forms of intuition, we should focus on what he called spatiality and temporality, the general concepts of spatial and temporal ordering as the truly fundamental Kantian categories.
Okay, I think I'm following. So it's not the specific geometric structure of space that matters, but rather this underlying concept of spatial relationships. And that concept, according to Bullard, remains a priori a necessary condition for our experience of the world.
Exactly. And he saw general relativity's dynamic space-time not as a refutation of Kant, but as an example of how our understanding of the objectivity of space and time has evolved and become more sophisticated over time. It was a bold reframing of the issue.
It's like general relativity forced them to peel back another layer of the Kantian onion, revealing a deeper level of critical idealism that could actually embrace these new discoveries.
That's a great analogy, but perhaps the most influential Kantian response came from Ernst Cassirer, a leading figure in the Marburg school of Neo-Kantianism. He saw general relativity as this crucial test for what he called Erkenntniskritik, the critical examination of knowledge.
And what was his verdict? Did general relativity pass the test?
Cassirer believed it did. He argued that general relativity, especially its emphasis on general covariance, actually confirmed Kant's core insights about the role of what he called intellectual forms in shaping our understanding of the world.
Can you remind us again what general covariance is and how Cassirer connected it to Kant's philosophy?
Yeah, so general covariance means that the laws of physics should be the same regardless of what coordinate system you use to describe them. In other words, the laws themselves shouldn't depend on our particular way of labeling points in space and time. It's about the inherent objectivity of the laws of physics.
Ah, I see. So just like how Kant said that space and time aren't things in themselves, but rather this framework through which we experience reality, general covariance seems to suggest that the laws of physics also transcend our particular perspective. They have this kind of universal validity.
Exactly. And Cassirer saw this as this profound validation of Kant's transcendental idealism. It wasn't that space and time were literally in our heads, but rather that our minds impose this certain order on experience, and that order, as evidenced by general covariance, is reflected in the very structure of the laws of physics.
So instead of seeing general relativity as this threat to Kantian thought, Cassirer saw it as this shining example of how these intellectual forms shape our knowledge, even at the most fundamental level of physics. That's a pretty powerful argument.
It is. And he went even further, arguing that general covariance pushed Kant's ideas even further by showing how the concept of an object in physics was evolving away from concrete individual things towards this more abstract and relational understanding.
So instead of thinking of objects as just things out there in space and time, we're moving toward this view where objects are defined by their relationships and interactions within the framework of these intellectual forms. It's like the whole notion of what constitutes an object is becoming more fluid and interconnected.
Precisely. And this shift, according to Cassirer, was this direct consequence of general relativity and its impact on our understanding of space, time, and the laws of physics. It was this truly remarkable philosophical insight.
It's amazing how a theory about gravity can lead to such deep philosophical insights about the nature of knowledge and reality itself. It It really shows how interconnected these different fields of inquiry are.
It really is.
Yeah.
Now, while the Machians and the Kantians were grappling with the implications of general relativity, another influential group of philosophers was also deeply engaged with Einstein's work.
Right.
They brought this very different perspective to the table.
I bet you're talking about the logical empiricists. This group, with their focus on logic and empirical observation, was really shaping the landscape of 20th century philosophy. I'm curious to hear how they interpreted general relativity.
They did, and they really saw in general relativity this powerful confirmation of their own views about the role of conventions in science. Their key figures, like Moritz Schlick, Rudolf Carnap, and Hans Reichenbach, they were all profoundly influenced by Einstein's theories, particularly his analysis of simultaneity in special relativity.
Right, the idea that the simultaneity of events isn't absolute but depends on the observer's frame of reference, that was a pretty big deal back then. It really shook things up.
It did, and the logical empiricists used it as a springboard to develop their broader philosophy of science, arguing that conventions, or coordinative definitions, as Reichenbach called them, they play this crucial role in linking theoretical concepts to observable phenomena.
So instead of seeing scientific concepts as directly reflecting some objective reality, they saw them as tools, frameworks that we use to organize and understand our observations. And these frameworks, according to them, inevitably involve choices, conventions that aren't dictated by nature itself. It's like saying that there's a human element, right, kind of built into the way we do science.
Exactly. And this idea that there's a degree of choice or conventionality in how we construct our scientific theories became a central tenet of logical empiricism. And general relativity, with its complex interplay between geometry, physics, and observation, provided this rich field for exploring these ideas.
Yeah, I can see how general relativity, with its flexible spacetime and its emphasis on the observer's frame of reference, would resonate with the logical empiricists' focus on conventionality and the role of observation in shaping our knowledge.
Absolutely. It was a perfect example of how even our most fundamental concepts of space and time could be understood as partly conventional, right? Chosen for their usefulness in organizing our experience rather than as representing some absolute pre-existing reality. It was a profound shift in perspective.
It seems like general relativity provided this fertile ground for philosophical debate across a wide range of schools of thought, right? It's like it cracked open this door to this whole new set of questions about the nature of reality, knowledge and the role of the human mind.
It certainly did. And what's even more fascinating is how these debates continue to this day, shaping our understanding of the relationship between physics, mathematics, and philosophy. But before we wrap things up, there's one more captivating philosophical aspect we need to cover the geometrization of physics and its implications for our understanding of reality.
Oh, I love it when things get a little meta. So tell me, how did general relativity spark this idea of geometrizing physics?
Well, you see, in general relativity, gravity is no longer seen as this force acting at a distance, like in Newton's theory. Instead, it's understood as this consequence of the curvature of space-time itself. This curvature is determined by the distribution of matter and energy, which in turn dictates how objects move. It's all beautifully interconnected.
So instead of thinking about gravity as this mysterious force pulling things together, we think about it as objects simply following the curves and contours of space-time, like marbles rolling on a warped surface.
That's a great analogy. And this success in describing gravity in geometrical terms led some physicists and philosophers to speculate that perhaps all of physics could be similarly geometrized.
Wait, so you're telling me that instead of thinking about forces, fields, and particles as these separate entities, we could imagine them all as manifestations of the geometry of some higher dimensional space? It's like the universe is one giant, intricate geometric pattern.
Exactly. This vision of geometrizing physics captured the imaginations of many thinkers in the early 20th century. It was this truly ambitious and daring idea.
That's a truly captivating vision. It sounds almost mystical, like some ancient Pythagorean dream of finding mathematical harmony at the heart of reality.
Right.
But did this geometrization program, as you called it, actually succeed? Did anyone manage to unify all of physics under the banner of geometry?
Well, there were some valiant attempts, but ultimately no one managed to pull it off. The most notable efforts came from Hermann Weyl, who developed a pure infinitesimal geometry, and Arthur Stanley Eddington, who proposed this comprehensive world geometry.
Those names ring a bell. Didn't they both incorporate electromagnetism into their geometric frameworks? That was a big part of the challenge, right? Unifying gravity and electromagnetism?
They did, but despite their ingenuity, their theories faced challenges and ultimately didn't gain widespread acceptance. The universe, it seems, is a bit more reluctant to reveal its secrets than some might have hoped.
It's interesting how Einstein, despite being the one who kind of sparked this geometrization frenzy, ended up being quite skeptical of the idea himself. He wasn't one to be easily swept up in the latest intellectual trends.
He wasn't. Einstein was always more focused on finding a unified theory of physics, regardless of whether it was based on geometry or some other framework. He was a pragmatist at heart.
I guess he wasn't one to get caught up in the philosophical hype, even if he was the one who started it. He was always grounded in the need for a theory that could explain the observed phenomena and make accurate predictions.
Exactly. For him, the ultimate test was whether a theory could stand up to the scrutiny of empirical evidence. But even though the geometrization program didn't achieve its ultimate goal of unifying physics, it did have this profound impact on the philosophy of science.
How so? What were some of the philosophical ripples it created?
Well, for one thing, it fueled discussions about the relationship between mathematics and physical reality. Some saw it as evidence for a kind of mathematical Platonism, the idea that mathematical structures exist independently of the human mind, and that the physical world is somehow a reflection or manifestation of these structures. It's a very deep and thought-provoking idea.
So the universe isn't just described by mathematics, it is mathematics.
Right.
That's quite a philosophical leap. It makes you wonder about the nature of reality itself.
It does. But others, like Weil and Eddington themselves, offered more nuanced interpretations, drawing on ideas from transcendental idealism and structuralism. They were trying to find a middle ground between a purely mathematical view of reality and a more experiential one.
Intriguing. It seems like this geometrization of physics idea opened up this whole new dimension to the age-old debate about the nature of reality and the role of human knowledge. It's like it had added this whole new layer of complexity to the philosophical landscape.
It certainly did, and the reverberations of those discussions continue to shape our understanding of physics and its philosophical foundations to this day. It's a testament to the enduring power of these ideas.
We've covered a lot of ground today. We journeyed from the positivist anxieties about the whole argument to the Kantian efforts to reconcile their philosophy with a dynamic space-time, and then into the grand visions of geometrizing all of physics. It's amazing how general relativity, a theory born from the study of gravity, has touched on so many fundamental questions about reality, knowledge, and the role of human thought in shaping our understanding of the universe.
It really is remarkable how general relativity's ripples extend far beyond physics, touching on the most fundamental questions we can ask about the nature of reality itself.
It makes you realize that science and philosophy aren't separate disciplines. They're intertwined in this incredible dance of discovery. It's not just about equations and experiments. It's about grappling with the big questions, the mysteries that have captivated thinkers for centuries.
Absolutely. And what strikes me about all these philosophical responses to general relativity is how they underscore the limits of our knowledge and this undeniable influence of our own conceptual frameworks in shaping how we understand the universe. It's a humbling realization.
So what does all of this mean for us, the non-physicists, the non-philosophers out there trying to make sense of it all? Is there a takeaway message, a nugget of wisdom we can glean from these complex philosophical debates?
I think one of the most important lessons is that even our most fundamental assumptions about the world, things we take for granted like space, time, and the laws of physics, they aren't set in stone. They're constantly being revised and reinterpreted as our knowledge grows and our perspectives evolve. It's a reminder to stay curious and open-minded.
It's a humbling thought, but also incredibly exciting. It means that the universe is far more mysterious and wondrous than we might have imagined, full of unexpected twists and turns. There's always more to learn, more to explore.
Precisely. And it underscores that the quest for knowledge, whether in science or philosophy, it's a never-ending journey. There are always more layers to peel back, more perspectives to consider. It's about embracing the unknown and finding joy in that process of discovery.
Well said. It's like General relativity threw open a door to this whole new realm of philosophical inquiry, and we're still wandering through its vast and uncharted territories, trying to make sense of this strange, beautiful landscape.
Exactly, and perhaps the most vital lesson we can draw from this is that the pursuit of knowledge should always be guided by curiosity, open-mindedness, and a willingness to challenge our own assumptions. That's what makes this intellectual adventure so rewarding.
On that note, I think it's time to wrap up this deep dive. But before we go, I want to leave our listeners with a final thought to ponder. We've talked a lot about how general relativity revolutionized our understanding of space and time, but what about the concept of causality? How does this theory, with its dynamic space-time and its emphasis on the observer's frame of reference, affect our understanding of cause and effect? It's a question that I think is worth exploring further.
That's a brilliant point. It highlights how, even as we delve into these mysteries of the cosmos, we inevitably end up reflecting on the nature of our own minds and the very foundations of human understanding.
Food for thought indeed.
Mhm.
Until next time, keep those deep dives going.